Welcome to my tutorial for the fourth lecture of the course Research in Financial Markets. And we have been discussing the paper on the performance of volatility management portfolios published in the Journal of Financial Economics. So what we want to do now is we want to implement a strategy like here given by equation 1. Yeah. So we will go through different factors, especially the Farmer and French factors, risk factors from the Farmer and French model, and we want to implement a volatility managed strategy by basically by dividing a certain scaling factor by an estimate or a forecast of a volatility. So we see here in equation 1 of this paper that the authors use an in-sample estimate for coming up with the scaling factor. So they want to have a scaling factor such that the volatility of the risk managed factor is the same as the volatility of the unscaled standard risk factor. Yeah, and they use here in equation 1 in an estimate of the realized volatility of the previous months of that factor here. And I told you already during the lectures that there are different estimates that one could use for coming up with a scaling factor. Yeah, so there are different papers and different approaches how to estimate this scaling factor here that you use to multiply the factor. Yeah, and this scaling factor here is basically it leverages or deleverages the position kept in this portfolio here, FT. So in our example that I will now show you, I have here an Excel file where I have data of the VIX, the VIX volatility. So if we go back to this paper, here they use past realized volatility, past realized factor volatility, in implementing the scaling factor here. So they weight basically, they use past realized volatility for estimating or for determining how much they would invest next period in this factor here. If they would either increase the amount, so which means leveraging the position, or decrease the amount, that is deleveraging the position. Yeah, so they would, based upon realized volatility, they would leverage the amount invested in this portfolio here whenever the past volatility in month t minus 1 is below the scaling factor C star, and they would deleverage the position whenever this estimate is above C star. Yeah. So in this example here, we use the closing price of VIX. So VIX basically, what we see here is in column B. So it gives you the last value of the VIX in January. Yeah. And what you get is the expected market volatility for the next month. So this is here a real forecast. Yeah. So this is not a real forecast actually. Yeah. It's they use a plain estimate of the former or previous realized volatility as an estimate for the expected volatility at time t plus 1. But what we do is we use a real expectation, because this is the real expected volatility, the market volatility, by using option implied volatility with the one month maturity, right? So this is a real expectation for the next month. So this here, we can plot also here the time series of VIX starting in January 1990, and our time series goes until obviously July 2019. So we have 355 observations of the data. So that's the VIX. We plot it here. We see this is the the VIX volatility, or the estimate, or the VIX of the end of month values. So we see here periods of high volatility and periods of low volatility that are alternating. So this is typical behavior of volatility. Obviously, that's the financial crisis period here. Yeah, we know the VIX has been very, very high, and here in the earlier part of the sample, we see the dot-com bubble formation, and in the early 2000s, basically when stock markets crashed worldwide, the VIX also was very high. So that's the VIX. So then we have here in columns H until M, we have the different risk factors. We have the market risk factor, we have the size factor, value factor, profitability factor, investment factor, and momentum factor. These are the risk factors of the Farmer and French 6-factor model. And obviously, these are also 6 of the 9 risk factors that have been investigated in this paper that we just discussed. So we see here in this row here, we see the volatility of the market factor in the sample period. And this 3.03 is the volatility of the size factor in that sample period. So that's basically what you see here in this row are the corresponding volatilities of these risk factors here. And as an estimate for the volatility, we use simply the standard deviation of this time series vector. So the question arises, so what we see here now, we have the risk managed strategies. We start with the market factor as here. The second is the risk managed SMV size factor. We have here in red the risk managed value factor, profitability factor, investment factor, and momentum factor. And maybe we can make it a little bit lighter because it's maybe not so easy to see. No, this was wrong. So let's use here a different color. Maybe we take green as well. So, and here below also we will take maybe green. Okay. So here we have the corresponding risk managed counterparts or volatility managed counterparts. So whenever we talk about risk management, it's a synonym for volatility managed. It's the same thing. So if we scroll down, below these column vectors, our time series vectors, we have here a table. Okay, so in this table we report for these corresponding factors here some statistical figures like the sample average, and here it's simply the average of each time series vector. Here we report the square root of the time series variance divided by the number of observations. So this is what we need for the t-statistic. It's the denominator of the t-statistic. So in the t-statistic, we have in the numerator the mean, so the sample average, divided by this number here, divided by the square root of the variance divided by the number of observations. So the t-statistic for the market factor given the sample period is obviously 2.91. And here you see the corresponding sample averages of the other factors as well. So as we see from this table here, only the profitability factor and the momentum factor actually generated statistically significant payoffs on a 5% level, as these t-statistics indicate or show a value higher than our critical value of 1.96. Okay. So, and here again we have the ex post volatility over the sample, the same number that we have seen here above. Well, it should be basically the same number. So then the question arises, how do we determine the scaling factor? So the scaling factor, once again, if we go back to the paper, equation 1 is scaling this, something is in the nominator of the scaling factor, the C star, and we have here this estimate the realized variance of time t-1. We use instead of the realized variance, we use simply the VIX of time t-1. We could also use the VIX squared, because the VIX is obviously the volatility, and if we square the VIX, what we get is the corresponding variance. But in our case, we are satisfied with the simple volatility. So the question arises, how do we determine the scaling factor, which is in the nominator? So basically, we can do it by try and error if you want. Okay, so we can basically we can start with 16, and what we would have here is the scaling factor divided by the first value of this scaling factor here, like this C star divided by a measure for the volatility, would be basically the scaling factor, which is here obviously in this field, in this blue field here, 16, divided by VIX. And actually, we want to have the adjusted closing price of the VIX, which is this guy here, right? So this would be the first value of our leveraging or deleveraging factor. And then we can double click, and then basically it gives us the corresponding estimates across time. So so we see we always divide every corresponding value here of the VIX divided. So we have it in the denominator of that factor here. It's this guy here. And in the numerator, we have this scaling factor C star. So this is C star, in our case 16, divided by the VIX. And what we have to do is, so again, this VIX at time t-1 gives us the forecasted volatility for the next period, which is this month here, February. So we have to multiply this scaling factor here. This is basically our leveraging or deleveraging factor, and in our case, we deleverage the position in the next month here. So what we have here is we have to multiply this guy, but it's the market return in the next month, we have to multiply it by this factor here, 0.63. So we deleverage the position kept in the market portfolio, which gives us 0.7 as corresponding return. And double click, so basically multiplies the corresponding leverage or deleveraging factor with the corresponding market return, and which gives us then the time series of the volatility managed portfolio. So if we can also plot the scaling factor across time. Let's plot the scaling factor across time. And what we see is, of course, a similar pattern as we saw with the volatility already. So we have periods where we leverage our position. We have here obviously leverage of the maximum leverage is here, obviously here, and this is 1.68. And we have here periods where we deleverage the position, where we just invest sort of 0.60% in the market portfolio, and the rest of our wealth, 40%, we put on our bank account. Here in this area, 140. So we invest 140% in the market portfolio. That means we leverage our position. So we invest more than 100% in the market portfolio. This is what it tells us. So obviously, a scaling factor is a C star of 16%, okay, would give us here a volatility of the risk-managed market factor of 3.3. The thing is now we want to have the same volatility of the risk-managed factor or volatility-managed factor than we have for the standard unscaled market factor. So how do we come from, what can we do in order to come to the same volatility of 4.25? So what we can do is, obviously, we have to increase a higher amount here. So let's try 16.5 as scaling factor. So what we would get here, obviously, the volatility of the volatility managed strategy would increase to 3.4. So we need to increase even more. So let's try 4.7. Now we have average volatility of 3.4. So we can now increase it even more. Let's increase it to 17.5. Now we come closer. Now it's 3.6. So we need to go even higher. Let's take 20. Now we are much closer. Now it's 4.12. Here we have 4.25. So we need a higher scaling factor, obviously. Let's take 22. Now we have overshooten it. Now it's 4.53. So we need a lower scaling factor. Let's take 21 instead. Now we have still too much. It's 4.33. Here it's 4.24. So we need obviously something like 20.4. Yeah, we are almost there. Let's try 20.6. And now we are actually there. So if we take 20.61, now it's basically, it's something in between 20.6 and 20.61. So if you basically take 20.6, this number here, if we round it, yeah, let's round these numbers here. So voila, it's actually rounded on two figures. Now we get the same volatility of the risk managed market factor as we have for the as we have for the standard market factor. Yeah, volatility is 4.25. Okay, so the corresponding scaling factor is obviously 20.6. So this number here, 20.6 for the market factor, if we use in our denominator the VIX, the adjusted closing price of the previous month's VIX. Okay, so if you scroll down now, we see that the market factor, obviously the risk managed market factor using VIX and this approach produces an average payoff, a mean of 0.8 compared to the unscaled market factor of 0.66. So risk managed market factor produces a higher average payoff than the unscaled market factor, which is also in line with the earlier paper of Moreira and Moore. Of course, the standard deviation or the square root of the variance divided by the number of observations, which is in essence the denominator of the t-statistic, it must be the same by construction because the volatility of our series is the same by construction. So this is just a rounding issue here, that it's here 4.24 and here it's 4.25. So it's basically the same. Okay, you see it here. So what do we next? You remember from this paper, so they regress the risk managed series on the standard series. And later on, they even control for the Parment branch factors. So that's what we also want to do now. Let's just copy this payoff series here in a new matrix, in a new Excel file. So let's call this vol MKT as volatility managed market factor. Let's copy also the corresponding time congruent vector of market returns, of unscaled market returns in the same to the same Excel file. Here we have the market return unscaled, and let's also take the corresponding size factor and value factor, because then we can also control, you can also run the regression for controlling for the Parment branch factors. So that's the SMB factor, and that's the HML factor, right? So let's store our Excel file here on the desktop. I will store it here on my desktop. Let's denote it as A, and denote it however you like. And we can close it again. Let's open Eviews. I have done it already here. So we also need to know the number of observations. So how many observations do we have? So obviously it's 354. Let's go back to Eviews, because Eviews will ask us now how many observations do we have. So let's go on File, New Work File. We use unstructured, undated. Of course, we also could use dated, but it's easier. It's just simpler to use just unstructured. So we have 354 observations. Push the OK button, and Eviews opens a new work file. Then we go on procs, import file from, or import from file, and then we go basically. We know we have it on the desktop. We know it's Excel sheet A. We go just on finish. No. And what we see is here we get our vectors that we want to have. Yeah, we have got the volatility-managed market factor, the standard market factor, size factor, and HML factor, the value factor. So what do we have to do? According to equation 2, we have to regress the volatility-managed factor on the intercept term and the standard unscaled market factor. So then the intercept term, if this guy is significantly positive, it means that using the volatility-managed factor increases or expands the mean variance frontier, ex post. Now remember, this is an ex post analysis. So go on new object, equation, okay. Then we plug in vol MKT, which is our volatility-managed factor, C, which denotes the intercept term, and MKT. Yeah? So push the OK button, and Eviews spits us out the corresponding regression equation. So what we see here is, okay, the market factor explains 88% of the variation of the volatility-managed factor. The loading against the market factor is 0.94, which is obviously not surprising because they're highly correlated. And the intercept term is 0.15. 0.15% per month is unexplained. So 0.15% per month return of the volatility-managed market factor is unexplained by the exposure against the unscaled or standard market factor. We see that the t-statistic of the alpha is 1.86. So on a standard 5% level, we would reject the null hypothesis that the volatility-managed factor generates alpha. Yeah, but now remember, we are using standard t-statistics. Okay, we use standard t-statistic. If we check our factor, how it looks like, let's take the descriptive statistics and tests, histogram and stats. What we see is, okay, kurtosis is close to normal, but the distribution is skewed. It's negatively skewed. The Jackpera tests, obviously, as we see here, rejects the null hypothesis of normally distributed random variable. Now the p-value is 0. And the same is probably for the market factor. I would be surprised if this would be not the case. Even here, the market factor, as we see, has even higher kurtosis. Yeah, so it's 4.25. So obviously, it's a fat-tailed distribution. If we take the resids, and we can also go on, if we go object, is it proc, make residual series, we get the regression residuals from that equation, can store it here. If you check now the regression residuals, we see the regression residuals have a kurtosis of 6.5. So they have they're highly fat-tailed distributions. Yeah. So obviously, it doesn't make much of a sense to use a standard normal distribution as for our critical values. What we can do is here we can use autocorrelation in heteroscedasticity robust T statistic. Yeah. And what we get is here, now we get even a higher value. So the p-value is increasing. So it's now even less significant. Yeah. But as we know, because the residuals have excess kurtosis, so obviously the critical values here are not actually valid, yeah, for our hypothesis test. But anyways, so we see that based upon the inference that we can make, if we go back and we take the standard or the ordinary T statistics, so we see on a 5% level, yeah, we would not reject null hypothesis that this alpha here is 0. Yeah. So obviously in this case, based on a 5% significance level, and given that our assumption is true and the residuals are normally distributed, then we would obviously say, or we would come to the conclusion that the volatility managed market factor does not increase does not expand the mean variance frontier. So what happens if we control for the farm and branch risk factors? So let's add in the equation SMB and HML. This is also what they do actually. If you go back to the paper, this is what they report in table, let's see. Let's scroll down. It's here. It's reported in table 3 and panel B. Yeah. So what we have just done before is this guy here. We have just regressed the volatility managed factor on the market factor, which they have done here. Yeah. Our sample period is much lower. Okay, so they have a much longer sample period, which might explain that they have a T statistic here that is larger than 1.96. Yeah, but we know already from the conclusion part that the intercept terms, yeah, the regression parameters are unstable, so they are sample specific. So this might also explain for why we don't get the same results. But now, as for now, let's just do the next step here, and let's control in the regression equation also for the size and the value factor, and let's see what happens. So this is what happens now. Let's again, as for now, let's assume that the residuals are normally distributed. Then we can make inference using the T statistic. So what happens now is we see that the intercept term is now 0.16, so 16% after controlling for the farm and branch 3-factor model, which contains market factor, size, and value factor. 0.16% of the volatility managed market return cannot be explained by the exposures against the farm and branch 3-factor model. The statistic of 2.01 indicates that we have to reject the null hypothesis that this point estimate here alpha is 0 because the p-value is below 0.05. The statistic indicates that this point estimate of 0.16 is significant on a 5% level. Yeah. Hence, using the volatility managed market factor expands the mean variance from frontier of these 3 factors here. Yeah? So adding the volatility managed factor, market factor, to these 3 risk factors here expands the mean variance frontier. This would be our conclusion. And this is basically also in line with what they have reported here. Yeah? So they have a point estimate, annualized point estimate of 5.2. And what we have is the is the monthly. So we have to multiply 0.16 with 12. This is basically what we supposed to do. Let's just do that in order to annualize this figure. 0.16 times 12. So our number is 1.92% per year. So it's lower than reported here in the paper, and our significance level is also lower. Yeah, it's still significant in our replication using the VIX. Yeah, we have 2.01 as a t-statistic. They have 3.49. Yeah, but anyways, based upon standard inference, we have qualitatively the same result. So in the same manner, we could do the same thing for the other factors here. Yeah. Then of course we would need to figure out what's the scaling factor. Again, we would need to figure out what's the scaling factor in order to have the same volatility as the corresponding unscaled factor. Yeah. So we would be supposed to compare the volatility of our volatility-managed factors with the volatility of the standard factors. Yeah, and so we have to choose the scaling factor by trial and error, for instance, that matches the corresponding volatilities. Yeah, like we did for the market factor, same thing. Yeah, this is what I would like to do with you in this short tutorial, so that you get a clue, or that you get a better idea about what all this is about. So again, as we discussed, so basically the out-of-sample experiment requires that we continuously re-estimate this model across the sample period. So we use a training period. They used 120 months as a training period, and then re-estimated the model, getting new parameters in each, or new regression parameters in each iteration. You remember that the regression alpha is important for the optimal weight allocation of the mean variance maximizing investor. So this is what we obviously cannot do in Eviews, but this is obviously something that we could easily implement in programs such as MATLAB or R. And this might be something that I will do this year in my quantitative finance course as well. Thank you for your attention.